So let's continue and let's start from slope and aspect. And let's read this question. What type of raster operation is slope function? So as you remember from the module raster operations, we have basically four types of raster operations, which can be divided into local, focal, zonal, and global. So when we take the pixel itself, not comparing to other pixels, neighboring pixels, or pixels which have the same value, etc., we work with local operations. We call this type of operation a local. But when we calculate the slope, actually, the neighboring pixels actually influence to each other, because we can calculate the slope of a pixel only when we compare these pixels with neighboring pixels. For instance, if the one pixel has the elevation of 50 meters and the neighboring pixel has the elevation of 30 meters, so we can just take into account these elevations. We can compare. We can calculate the slope of the pixel which has the 30 meters slope. So in this case we compare with neighboring pixels in this therefore the slope is belongs to focal types of operations. Go to the spatial analysis tool, surface slope, choose dam interpolation you made before and choose degrees. So okay, now we will make a slope interpolation and surface, and here we have slope. So which kind of which kind of interpolation you going to choose? I prefer to choose the first one. I will close this one, and I prefer to choose this one because it's approximately close to the values of the input vector. So okay, let's open the slope and go to IDW power 2 degrees, where we will measure the slope in degrees. You can also measure in percent. For instance, if your pixel has the elevation of, in this case, right, 50 meters, and the neighboring will have the 30 meters, so the slope will be in percent is 50%, right? 50%. While in degrees, I suppose it will be 45 degrees. Okay, let's first go to the planner, method planner. And z factor optional is 1. So if you put 1, if you go, for instance, you're measuring in meters, right, and you also want to interpolate slope in meters itself, the z value 1 means that it also will be calculated in those units which have the x and y coordinates, number of ground x and y units in one surface z unit. Okay, so also do not forget to put the region and the extent and mask region also, region. Okay, now so z unit in meters. If we choose in if we change the z value to, for instance, 10 or 100, it will be calculated in other units. So this is our slope. We can cut it with snip tool, or you can make a print screen with table of contents. So actually I just accidentally go to the answer to question 7. So slope, here we can see the degrees, right? So let's go and just see what kind of values it has. So its slope is minimum is 0 degrees and maximum is 90 degrees, right? So it's total vertical slope in this case. So okay, IDW here. So this slope is actually not the real slope of the surface, but it's approximation of the slope which is dedicated from the IDW interpolation method. So what is the real slope? Actually, it's hard to understand because it depends on various factors. As I said before, it depends on the method of interpolation, it depends on the accuracy of your measurement, it depends on the number of points you measure, etc. But we will talk further in the following modules. Mostly today people use, and just GIS specialists and remote sensing specialists use the Aster digital elevation model, which has also the spatial resolution of 30 meters, and it's actually very close approximation of the Earth's surface of the Earth's elevation model, because 30 meters is good for slope, because within 30 meters, so it's 900 square meters of 1 pixel. In this area, slope doesn't change very fastly, very low, high. So this area has a very high slope, so we can just change the number of classes into 5, right? So it will be easier to know. Let's classify them using equal interval, right? So we can see from the area that this area, according to the interpolation, the point observations, has a very terrain area, because it lies within a slope from 0 to 15 degrees. So it's a flat area, very flat area, while the steepest areas here is this and this. So I think that I chose a very not 10, better to choose natural breaks. Okay, natural breaks. Okay, so we'll talk about this type of classification and symbology, all of this in the further lectures and further topics. So we'll talk about the natural breaks, equal interval, defined quantile, etc. So here is our slope areas. So these areas are steep, red one, right? These areas have a moderate steepness, and these areas are really flat. So this is 1 degree of slope, this is 10 degrees of slope. We can make them even closer, right, just to distinguish 1 pixel. Okay, here 2 neighboring pixels, right, which differ in slope. This is 11 degrees and this is 14 degrees. So just class just 3 degrees of difference, but this one also differ, also 2 degrees, I think. So now let's close remember this area, and close slope, and compare the elevation. So it's we can remember that we can choose all visible layers here in order to compare. So the slope of the area is 14 degrees and the elevation is 460 meters. Here is 10 degrees, 418 meters. So the difference in 4 degrees made only 3 meters of difference. But it's depend on the interpolation method. Actually, you should remember this. We could gain then another values from the interpolation method, and which type of interpolation method is the best. We also will talk on the following model. After this model, which interpolation method is the best for calculating and the slope and aspect, and for also making the surface analysis. This is mostly a kriging method, and we also will use geostatistical tools for calculating for making a surface analysis. So okay, write down the maximum, minimum, and average of slope gradient. So the maximum minimum we can find here in this source. Minimum is okay, we can write that its minimum is the minimum is 0 degrees, and maximum is I think it was 78 degrees. So 78 degrees, actually it's a very very steep area. Go to spatial analysis tools, surface aspect, and calculate aspect of slope. And last one, we will calculate the aspect of this area. It also within a surface analysis. So aspect that derives the aspect identifies the compass direction that the downhill slope faces for each location. So I want to calculate the aspect for the same IDW power and using the planar method. So we talked during the lecture what is the planar method mean. There are two types of calculating aspect, planar and geodetic. So we will choose planar and we will choose region and raster analysis. Okay, let's calculate the aspect. So it calculates the direction, the compass direction of the downhill slope, which the downhill slope faces. So this is our beautiful output image. Let's close this one, and we can just make a print screen to show not only the map itself but also the classes. So this is flat. So how many flat areas we have? So aspect is also the continuous raster, and actually these classes represent the degrees from, for instance, north 0 22.5 degrees, and the north also red. We can change the well, let's not change. Okay, north is 337 degrees, 360 degrees, etc. So aspect operation also belongs to the focal types of operations, because it works with 3 and 3, in general 9 neighboring pixels, and it shows the direction of compass the surface is facing at that moment. For instance, this and these areas are facing north, and for instance, and these areas are facing northeast. You can apply aspect tool during for many types of GIS analysis. For instance, the hydrological analysis, hazard analysis, and for calculating the area which gains much more sunlight than others, etc. This is the end of our second part of our tutorial 8, and let's continue with isolines on the following video.